Look around you. The bristles on your toothbrush, the casing of your phone, even the shirt on your back. Chances are they share a secret origin. They aren't grown in a field or sheared from an animal. They are pulled from the ground as crude oil. For most of human history, the materials we used every day were strictly limited by what nature could produce. If you wanted a warm coat, a sheep had to grow the wool. Cotton shrank when you washed it, and harvesting silk required boiling thousands of tiny insect cocoons. As global populations grew, so did the demand for fabrics that were cheaper, stronger, and easier to mass produce. Waiting on the slow biological cycles of plants and animals was a bottleneck we had to bypass. To outpace biology, scientists turned to chemistry. They realized that instead of harvesting ready-made fibers, they could extract raw petrochemicals and build entirely new materials, molecule by molecule. This engineering relies on a tiny structure called a monomer. Think of it as a single link in a chain. By applying specific heat and pressure, chemists force them to snap together, creating a massive structure known as a polymer. Because these polymer chains are so long, they can be melted down, forced through tiny holes, and drawn out into continuous, solid threads. We can then take those artificial threads and weave them exactly like traditional cotton or silk. We were no longer limited by the resources the earth naturally provided. By snapping chemical links together in a lab, we began engineering materials to solve specific problems. The early successes replaced our most expensive textiles. Scientists dissolved wood pulp and forced it through acid baths to create rayon, a cheap artificial silk. Later, they extruded dissolved petrochemicals into warm air to spin acrylic, a highly effective substitute for heavy winter wool. The true test of these new capabilities came with nylon. Engineered from coal, water, and air, this polymer yielded a fiber that was incredibly elastic, virtually weightless, and exceptionally strong. That strength made it an immediate military priority during World War II. Paratroopers relied on those massive canopies, which required a durable alternative to imported Asian silk. The military demand was so intense that nylon disappeared from consumer markets. Women across the country answered calls from store signs like this one, donating their sheer hosiery to be melted down and respun into powder bags and tow ropes. Post-war, the industry evolved beyond pure synthetics and invented blending. By weaving a synthetic like polyester together with natural cotton, you get a hybrid fabric that combines the breathability of a plant with the wrinkle-free resilience of a plastic. By mixing and matching these chemical chains, we created textiles tailored for extreme environments. A natural cotton rope snaps under heavy tension. A nylon climbing rope holds fast. This molecular control rapidly expanded beyond woven fabrics. By tweaking the chemical structure, scientists learned to pour and cast rigid objects. It all comes down to how the polymer chains are arranged. In materials known as thermoplastics, the chains are long and linear, freely sliding past one another. Because they aren't permanently tethered together, you can apply heat to weaken their grip. The plastic melts into a liquid, you press it into a new mold, and it solidifies as it cools. You can repeat this process indefinitely. But if you introduce chemical bridges that bond those parallel chains together, you create a thermosetting plastic. The material is now a single, three-dimensional grid. Once that grid sets, the crosslinks are permanent. No amount of standard reheating will melt it. The plastic will simply char and burn. That thermal stability makes it an excellent insulator for high-voltage electricity and severe heat. That's why early thermosetting plastics like Bakelite were universally adopted. It was the perfect material to form the chassis of this vintage radio casing, and it's why the handles on hot skillets don't melt on your stove today. With just two structural designs, sliding chains for flexibility and locked grids for permanence, we developed a library of materials built to withstand nearly anything. But there is a catch to engineering a material to resist the elements. The exact properties that make polymers so valuable, they are immune to bacteria, highly stable, and practically indestructible, are the reasons they are accumulating so rapidly. We took synthetic structures capable of surviving for centuries and applied them to items we intend to use for 3 minutes. A plastic wrapper is engineered for eternity, but discarded instantly. When you throw away an apple core or a wool shirt, microorganisms break them down. But nature has almost no biological tools to disassemble a synthetic polymer chain. Those plastics set in landfills and soils for hundreds of years, slowly fragmenting. Eventually, they spill over into local ecosystems. In urban areas, wandering wildlife inevitably consumes this synthetic waste, clogging their digestive tracts with indigestible films. Even when left untouched by animals, the sheer physical volume overwhelms our cities. Entire drainage canals become structurally blocked by thousands of bottles, causing severe flooding. We designed materials to outlast biology, and we succeeded perfectly. We have left behind a permanent, fossilized layer of human waste woven directly into the planet's surface. We can't go back to relying exclusively on cotton, silk, and wool. Synthetics are required to support modern medicine, transportation, and construction, but we can change how we manage the waste. If you check the bottom of a plastic container, you'll usually find a numbered triangle. This is a resin identification code. It functions as a chemical blueprint, telling a recycling facility exactly how much heat is needed to melt and remold that specific polymer. Navigating this requires a strict set of priorities. First, reduce the volume of single-use polymers. Reuse the rigid plastics that already exist. Recycle the thermoplastics using those specific resin codes. And recover energy or raw materials from whatever is left over. The synthetic age was built in a laboratory, molecule by molecule. Knowing exactly what those molecules are and how they behave is the only way we stop them from burying us.